Okay, so that represented a kind of high-level overview about this module, as well as other aspects that we're going to touch upon in this course. But now let's delve into this specific case of simple linear regression and talk about what this means. So going back to our flowchart, what we're going to talk about now is specifically the machine learning model. So that's that highlighted green box, and everything else is grayed out. So you can forget about everything else for now. We're just talking about our model and what form it takes. So our simple linear regression model is just that. It's very simple. We're assuming we have just one input, which in this case is square feet of the house, and one output, which is the house sales price. And we're just going to fit a line, a very simple function here, not that quadratic function or higher order polynomials we talked about before, just a very simple line. And what's the equation of a line? Well, it's just intercept plus slope times our variable of interest. So that we're going to say that's W0 plus W1x. And what this regression model then specifies is that each one of our observations, yi, is simply that function evaluated at xi, so that's W0 plus W1xi, plus the error term, which we called epsilon I. So this is our regression model. And to be clear, this error, epsilon I, is the distance from our specific observation back down to the line. Okay, so the parameters of this model are W0 and W1 are intercept and slope, and we call these the regression coefficients. So that summarizes our simple linear regression model. Very straightforward, very simple, but we'll get to more complicated things later. Okay, well, working with the simple linear regression model, let's talk about how we're going to fit a line to data. But before we talk about specific algorithms for fitting, we need to talk about how we're going to measure the quality of a fit. So we're going to talk about this orange box here, which is this quality metric. And in this case, now that we've mentioned that our function is parameterized in terms of some parameters we're calling W, that represents W0 and W1 in this case, our intercept and our slope. We know that when we're going to predict house values, instead of talking about f hat, our estimated function, we can talk in terms of w hat, our estimated parameters, because those estimated parameters fully determine our estimated function. So we're going to modify this block diagram and replace f hat now with w hat and talk about estimating these parameters w. So what's the cost of using a specific line? Well, the one we're going to talk about here, and the one that we focused on in the first course of the specialization, is residual sum of squares. And what residual sum of squares assumes is that we're just going to add up the errors we made between this line here, which represents what we believe the relationship is and what we've estimated the relationship to be between x and y, and what the actual observation y was. So we're going to take each one of these errors or residuals and sorry, I should be clear. I talked about error as the epsilon I. The error was part of my model. A residual is a difference between a prediction and an actual value. Okay, so I want to make sure that that's clear. So that's why this is called residual sum of squares. So this is the formula that we presented in the first course of the specialization. So I'll run through it fairly quickly. Our residual sum of squares is going to be a function of our two parameters, W0 and W1. That determines what line we're looking at. So of course, as I change that line, we're changing the cost, this cost term RSS. And what I'm doing is I'm adding up the difference between the specific house sales price of a given house and what my line specifies it as. And what does the line specify the price to be? Well, it specifies it as W0 plus W1 times however many square feet this house had. But I'm not just looking at that difference, nor its absolute value. I'm looking at the square of the difference. That's where the sum of squares comes in. Well, that's where the squares comes in, and then the sum is I'm adding over this error over all houses in my training data set. Okay, so just to summarize, residual sum of squares is I take this difference between what the line is telling me the price of the house should be, what the actual house price was, look at that difference, square it, and add over every house in my training data set. So we saw this equation before, but now I'm going to write it more compactly, and we're going to work with this form throughout the rest of this module and forms like this in the rest of the course, where I've introduced this notation, this capital sigma, where what this means is if I write sigma and I write an I equals 1 on the bottom of this Greek letter and a capital N at the top of this Greek letter, then what I'm saying is I'm summing over some quantity. I'll just generically look at some quantity AI. I'm summing A1 plus A2 plus all the way up to AN. So I'm summing up N different quantities. And in this case, here, what is AI? Well, AI is just this inner thing here. So it's yi minus w0 plus w1 xi quantity squared. Okay, so this is just shorthand notation for what we had on the previous slide where we're summing over all houses in the training data set, but instead of writing this thing in English or writing out this really, really massive sum over thousands and thousands of houses, I'm going to write it compactly like this. Okay, so now that we have this notation, let's talk about how we think about finding the best line. So we have this function that if you give me any W0 and W1, it defines a specific cost. So for example, this line, let's say the intercept was 0.97 and the slope was 0.85. Well, that results in some RSS. So I'll call this some, let's call it just number 1. And then if I give you a different line, so that's specified by a different intercept and a different slope, that's going to result in a different cost. So I'll just say that's some other number. And then this other line with different parameters has some other number associated with its cost as well. And my goal here, when I'm talking about estimating a function from data given a specific model, which in this case is just a simple line, is I'm going to search over all possible lines, all W0 and W1, so shifting this line up and down and looking at different slopes, and I'm going to try and find the one that results in the smallest residual sum of squares. So out of these 3 lines, if those were the space of all lines I was looking at, clearly it's not, it's a huge space I'm looking at, I would choose the one with the smallest number here. Okay, so we've talked about this simple linear regression model, just a line. And then we talked about how our goal in fitting this model is going to be to search over all possible lines and find the line that minimizes the residual sum of squares. We haven't talked about how we're going to do that. That's going to come next. We're going to talk about specific algorithms for searching over all possible lines to minimize residual sum of squares. But right now, let's just assume that we have some fitted line, and let's talk about how we're going to use it and how we can interpret the parameters. Let's start by contrasting the model from the fitted line. So our model, which I've written again here, is in terms of parameters. These are parameters. They're unknown variables of our model. And our goal is to estimate these parameters, fix values of these variables based on our data. And so that's what W hat represents. These are our estimated parameters. And these take actual values. So for example, maybe our intercept is minus 44,850 and our slope is 280.76. And these aren't random numbers that I generated here. This comes from the first course. If you look at the notebook for doing the regression fit of sales price on square feet, these were the numbers that came out for these two parameters. Okay, so these estimated parameters define a specific line. Okay, that's what this is. This line represents minus 44,850 plus 280.76 times x. So a model is in terms of some parameters, and a fitted line is a specific example within that model class. So it's a specific line. Now let's talk about how we can think about using our fitted line. So one thing that we can ask is to predict the value of this house that we'd like to list for sale. So this house has some number of square feet, and we'd like to guess the price. And how are we going to guess the price? Well, it's very straightforward. We're just going to plug into our fitted line. And so we're going to take the square feet of this house, which is represented here, plug that into the equation of this line, and that's going to produce our estimated value of the house right here. I want to mention one more thing here. So I want to mention that y hat, that's our predicted value of the house. Y hat is exactly equal to f hat of x. Okay, our model, remember our model said that yi is approximately equal to f of xi. But when we go to do a prediction y hat, that's exactly equal to f hat of x. And why is that? That's because the error is equally likely to be above or below the line. And f hat represents our best guess of the line given our data. And so if we want to guess the value of the house, we're unsure if that error for that specific house was above or below the line. So our best guess is to put it exactly on the line. Well, I can use this fitted line also if I'm a buyer, not just if I'm a seller interested in listing my house for sale. So for example, what I mean here is that I might have some amount of money that I can spend on a house, and I want to know how big of a house can I expect to purchase with that amount of money. Well, instead of estimating or predicting the value of the house, I can think of predicting the square feet. So just using this equation in reverse. So I have some amount of money in the bank, and that's going to be dollars in bank is this. And then I'm going to look at how many square feet I believe that I can purchase with that amount of money. Okay, so let's just go through a concrete example. Here's the fitted regression line I talked about before. So it's minus 44,850 plus 280.76 times x. And what I'd like to do is predict the value of a house that has 2,640 square feet. So what I do is just plug in 2,640 into this equation. That's my y hat. And that comes out to be, if you do that calculation, $696,356. Likewise, I can say, well, I want to predict how many square feet of house I can purchase if I have $859,000 to spend on the house. So if you do this calculation, you get that you can afford a house, or you expect to buy a house that's roughly 3,219 square feet. Okay, so now let's talk about how we're going to interpret the coefficients of our fitted line. And let's start by talking about w hat 0, our estimated intercept. So that's this point right here, this green star. And what does that represent? Well, it's the predicted value of a house with 0 square feet. So we can think of that as just land, because we have that y hat is equal to w hat 0 when x equals 0. So when there's no square feet, we have that our predicted house value is exactly equal to w hat 0. But I'll say that in general, this is not normally that meaningful. In many scenarios, you don't really think of having no input and having the output have some meaningful value. And actually, in our case, if you go back and look at the number, we had that our intercept was minus 44,850. So it's saying that land, you should actually, as the seller, be giving the buyer money to take that land off your hands. But remember that our data set's really noisy. It's not a perfect model of what's going on. So of course we have to think about interpreting our parameters in the context of what we've included in our model. Okay, we'll talk more about that in the next module, but I also want to talk about w hat 1, which is our estimated slope, and that tends to have a bit more meaning associated with it. So the estimated slope, I'm highlighting with this green triangle here, saying that per unit change in our input, so for 1 unit, so 1 square foot, what's our predicted change in the value of the house. So for example, let's say I'm looking at estimating the value of a house with 1,001 square feet. And I want to look at the difference relative to the estimated value of a house with just 1,000 square feet. Well, what is this? This is equal to, if I look at the first term, estimating a house with 1,001 square feet, how would I estimate that? I'd take w hat 0 plus w hat 1 times 1,001 square feet. And then I'm going to subtract, for the second term, I have its estimated value is, again, w hat 0 plus w hat 1 times 1,000 square feet. And these w hat 0s are going to cancel, and the difference between these numbers is just 1, so this will just be w hat 1. So again, w hat 1 represents the predicted change in the output per unit change in the input. Okay, so that's how we're going to interpret w hat 1. But one thing I want to make very, very clear is that the magnitude of this slope depends both on the units of our input and on the units of our output. So in this case, the units of slope are square feet per, are dollars per square feet. And so if I gave you a house that was measured in some other unit, then this coefficient would no longer be appropriate for that. So let's make this a little bit more explicit. So now that we know that there are units attached to these numbers, I'm going to put these in. So our intercept has units just dollars. So let me be clear what I'm actually highlighting here. The intercept has units dollars, and the slope has units dollars per square feet. And when I went through and did my calculation of predicting the value of a house with a given square feet, if I actually put in these units, I see that everything works out. Here I have dollars, here I have dollars per square feet, and then I'm multiplying by square feet. So when I multiply these two things, the resulting units of this is just going to be dollars. So the end result is something in terms of dollars. That's great. And likewise, when I use the equation in reverse, I have dollars divided by dollars per square feet, and I end up with something that's in square feet. So I'll just say units work out, which is great. But what if the house was measured in square meters instead of square feet? Well, clearly I can't just plug into that equation. And likewise, what if the price was measured in Chinese yuan instead of in US dollars? Again, can't just plug into that equation. So when I think about the magnitude, it only has meaning in terms of the units that I've used for my input and output.